Welcome to session 9 of the problem solving digital electronics problem solving course on IEEE. I'm your instructor Sachin Sampath from the Indian Institute of Science. Last class we started with chapter 5. We covered one problem. So we'll be covering more problems from chapter 5 in this class. We'll start off with problem 5.2. I'll just write down the problems. I won't be reading them out aloud. And then I'll explain the solution out loud. The question is asking us to make a JK flip-flop using a D flip-flop and a multiplexer, 2:1 multiplexer and an inverter. A D flip-flop will just, after a clock pulse, whatever is at the input of the D flip-flop will be reflected at the output of the D flip-flop. So if D is equal to 0, then Q will be 0 after a clock pulse. If D is 1 after a clock, before the clock pulse arrives, once the clock pulse arrives, Q will be equal to 1. So get it to operate like a JK flip-flop. In a JK flip-flop, when J and K are both 0, the previous state must be preserved. And J is 0, K is 1, then Q must be 0. When J is 1, K is 0, Q must be 1. And when J is 1, K is 1, Q must toggle. So if it was 1 earlier, it should become 0, and if it's 0 earlier, it should become a 1. Let's write the truth table. We have inputs J and K and D. So we use the multiplexer to form a combinational circuit to give the input to the D flip-flop, and the logic at the input to the D flip-flop should be the output of the multiplexer. So when J is K is 0, the previous state must be preserved. So the input to the D flip-flop must be the previous state Q. When J, K are 0, 1, input should to the D flip-flop should be a 0, because we want the output to be 0. Input is 1 0, jk is 1 0. We want the output to be 1, so we give the input to the D flip flop as 1. And when j and k are 1 1, we want the input to the D flip flop to be q complement, so that after a clock pulse the output will be toggled. So D can be written as j bar k bar q plus jk bar plus jk q bar. This can be further simplified by taking the j outside. You'll get k bar plus k q bar, that you can write as k bar plus k into k bar plus q bar. Now you can take out the k bar common in these two terms, and you can use the distributive law to write this as k bar into j plus j bar into j plus q. This will turn out to be j k bar plus q k bar plus j q bar. But this might not be the, let me check. This might not be the simplified form that we want. So let me simplify this using a k map. This is here j k, this is j bar j, k bar k, a q here, 0, 1 and a q bar. This 1 can be written as q plus q bar. So let me write that q plus q bar. You can form a pair between q bars here and form a pair between the q's here. Then you'll be left with, so in the blue group J bar is changing to J, so it is eliminated. You will be left with K bar Q. In the pink group, K bar is changing to K, so K is eliminated, and you are left with J, so it's J Q bar. So D should be K bar Q plus J Q bar. We had an extra term when I try to simplify it directly. We had a JK or something term, but most simplified form is this. So now this looks like if Q is the select line, then you would get S S0 bar I0 plus S0 I1, which is the output of a 2:1 multiplexer, where S0 is the select line and I0 I1 are the input lines. So that's what we will do. Use the 2:1 mux we are given. This is I0, this is I1. To I0 you give to I0 you give J, and to I1 we give K bar. So we have used the inverter. They said we can use a multiplexer and an inverter, followed by a D flip flop. The output Q of the D flip flop is fed as the select line. So this will turn the D flip flop into a JK flip flop. We'll go to problem 5.3. Show that we'll solve it via a K-map. We have J on this side, KQ on this side. Here is the truth table for this. There are 8 possible input combinations for J, K, and Q. When J and K are 0 and 0, Q of t plus 1 is simply Q of t. So Q bar of t plus 1 will be complement of Q of t. So you'll have 1 0 here. So this is a 1, this is a 0. When J and K are 0 1, the output Q of t plus 1 should be 0. So output Q bar of t plus 1 will be 1. And J and K are 1 0, output should be 1. Q of t plus 1 should be 1. So Q bar of t plus 1 should be 0. And J and K are 1 and 1, Q of t should toggle. So 0 should go to 1, 1 should go to 0. But Q bar of, that means Q bar of t plus 1 will also toggle. And Q bar of t plus 1, if Q of t was 0, Q bar of t was 1. So that will go to 0. Similarly, Q bar of t plus 1 will go to 1 when Q of t is 1 and you give J, K is equal to 1 1. We have two pairs here. This pair, the pink pair and the blue pair. That will give us Q bar of t plus 1 is equal to KQ, that's the pink pair, J bar Q bar, that's the blue pair, which is what they wanted us to show. We'll move up to problem 5.4. this is the excitation. This is the characteristic table. You have inputs P and N. You have the output state Q at time t plus 1 after a clock pulse. So if P and N are 0 0, then output must be cleared to 0. P and N are 0 1, there must be no change to the output, so Q of t plus 1 should be equal to Q of t. If P and N are 1 0, then we must complement. So Q of t plus 1 should be the complement of Q of t, and when P and N are 1 1, we must set to 1. So that is the characteristic table. Next we have to derive the characteristic equation. For that, we'll slightly change the table and write down Q of t also as one of the inputs. So when P and N are 0, regardless of the value of Q of t, you should clear to 0. When P and N are 0 1, you should preserve the state. So when P and N are 1 0, you should complement the state. When P and N are 1 1, regardless of the value of Q of t, you should set to 1. That is the truth table, considering Q of t also as an input. Now we'll get the characteristic equation, simplified version of it. Using a K-map. Again, here there are two pairs, which will give rise to the characteristic equation. Q of t plus 1 is equal to, from the pink pair we get n Q of t, and from the blue pair we get p Q of t complement. In part C, they want us to give the excitation table, that is, given Q of t, given the value of Q of t, if you want Q of t plus 1 to be a particular value, what should be your inputs P and N? That is, if Q of t is 0 and you want to get Q of t plus 1 to as 0, what should be P and N be? If it is 0 and you want to get 1, or if it is 1 you want to get 0, if it is 1 you want to stay at 1, you want it to stay at 1, what should be the input combinations that you give? Now from 0, if you want to go to 0, you can either clear or you can retain the previous state. So to clear, you can give 0 0, or you can retain the previous state by giving 0 1. In both cases, when Q of t is 0, Q of t plus 1 will be 0. That means as long as both these input combinations will do that. So in both those input combinations, P is 0, in one of them N is 0, and the other N is 1. That means regardless of the value of N, as long as P is 0, If q of t is 0, q of t plus 1 will be 0. So this is 0 and we don't care about n. Similarly, from 0, if you want to get a 1, you should either set it to 1 or you should toggle. To toggle, you have to give 1 0. To set it to 1, you have to give 1 1. So it's 1x. From 1, if you want to go to 0, you should either toggle or clear. So you should give 0 0 or 1 0. So you have to give 0 at n, and p can be anything. So it's x 0. And from 1, if you want to go to 1, you should either preserve the state 0 0 or you should set to 1 1 1. No, when you preserve the state, you have to give 0 1, or you can set it to 1 by giving 1 1. So it's x 1. P can be 0 or 1 as long as n is 1. That is the excitation table. How do we convert this PN flip flop to a D flip flop? We can see that if you want to get the output 0, you can give 0 0 to Pn, and if you want to get output 1, you can give 1 1 to Pn. But in a D flip flop, if D is 0, you have to get a 0, and if D is 1, you have to get a 1. So you can directly connect D to both P and N. So when D is 0, you want to get a 0. So if you connect both P and N to D, then P and N both will be 0 and you will get 0 output. Similarly, if D is 1, you want to get output 1. So if you connect both P and N to 1, your input to the PN flip flop will be 1 1 and the output will be 1. So to get a D flip flop, connect P and N together and treat it as the D input. In other words, you have your PN flip flop here. You have the clock signal, the output Q, tie P and N together and treat it as your D input. This will turn it into a D flip flop. Problem 5.5. This is a theoretical question, so I'll skip this. We'll go to problem 5.6. There are two D flip flops. That's the D flip flop whose output is A. That's the second D flip flop whose output is B. A of t plus 1 is xy bar plus xb. So you take B and it with xb, and you take x and it with y bar, that's xy bar. You OR these two together and give that as the input to the first D flip flop. B of t plus 1 is simply xa plus xb bar. So we take x and b bar and them together to get xb bar, and we take x and a and them together to get xa, or them to get xa plus xb bar. And finally the output z is simply a. All right. Part B, we have to list the state table for the circuit. State AB at time t, depending on input xy, you will get the state A of t plus 1, B of t plus 1. A of t plus 1 is xy bar plus xb, that is x into y bar plus b. So if x is 0, A of t plus 1 will be 0. If x is 1, A of t plus 1 will be equal to y bar plus b. So if y is 0, it will be equal to 1, or if b is 1, it will be equal to 1. So either y is 0 or b should be equal to 1. 0 otherwise, if both y is 1 and b is 0. That's A of t plus 1. B of t plus 1 is x into A plus b bar. So if x is 0, again A of t plus 1 is 0. If x is 1, B of t plus 1 is A plus b bar. So if A is 1, it's 1. If A is 0 but B is 0, it's 1. If A is 0, B is 1, and x is 1, it will be 0. That is the state table. 0 0 will go to 0 0 0 0. If xy is 0 0 0 will go to 0 0. If xy is 0 1, 0 0 will go to 1 0, 1 1 if xy is 1 0, and so on. And we have to draw the corresponding state diagram. There are 4 possible states for AB. You can be in state 0 0, be in state 0 0, 0 1, 1 0, or 1 1. If you are in state 0 0, you will stay in state 0 0 if your inputs are 0 0 or 0 1. Of course, here the output Z is simply A, so it depends only on the state it is in. So output is 1, output is 0 if A is 0. So this state is 0 1 slash 0. This state is 0 0/0. This is 1 0/1 because A is 1, and 1 1/1 because A is 1. So the output will go from 0 0 to 0 0 itself when xy is 0 0 or 0 1. So 0 0 or 0 1. It will go to 1 1 if you give 1 0 1 0. It will go to 0 1 if you give 1 1. Now from the state 0 1, you will go to 0 0 if you give 0 0 or 0 1. You will go to 1 0 if you give 1 0 or 1 1. Now from state 1 0, you will go to 0 0 for 0 0 or 0 1. You will go to 1 1 if you give 1 0. You will go to 0 1 if you give 1 1. From 1 1 you will go to 0 0 if you give 0 0 or 0 1. It will stay in 1 1 if you give 1 0 or 1 1. So that would be the state diagram for this particular circuit. Problem 5.7. A sequential circuit has For a full adder, the sum is XOR of the inputs. Here the inputs are X, Y, and Q. And the carry is XY plus XQ of t plus YQ of t, which is nothing but the input to the D flip flop. So this will be equal to Q of t plus 1. So we can write the state table as follows. Have the present state, inputs, the next state, and the output. We can see that the output is not just the function of the current state but also a function of the inputs. Present state is Q of t, next state is Q of t plus 1, inputs are X and Y, output is S. Since there are two possible present states, 0 or 1, and for each of the states there are four possible input combinations: 0 0 0 1 1 0 1 1. The next state Q of t plus 1 is simply xy. So if xy is 1 1, you will have a 1 plus xq of t. So if x and q of t are 1 and 1, we will have a 1 plus yq of t. So if y and q of t are 1 and 1, you will have a 1. And q of t plus 1 will be 0 in the remaining state and input combinations. And the sum you can see is the XOR of x, y, and q of t. So 0 1 1 0 1 0 0 1. That is the first part, the state table. Now we draw the state diagram from this. There are only two states, 0 and 1. So from 0 you can either go to 0 or you can stay in 0 or go to 1. We see that from 0 you will go to 1 only if the inputs are xy. Only if the inputs xy are 1 1, and corresponding to that the output will be 0. Similarly, you will go from 1 to 0 only if the inputs are 0 0, the corresponding output is 1. In all other cases you will stay in the same state. So for 0 0 with output 0, 0 1 with output 1, 1 0 with output 1, you stay in 0 state itself. And for 0 1 with output 0, 1 0 with output 0, and 1 1 with output 1, you stay in state 1 itself. So we are halfway through the session, so I'll take a break and come back in a few minutes. Let us move on to problem 5.8. Derive the state table and state diagram of the circuit shown below. There are two T flip-flops connected to the same clock. Input of the output of the first flip-flop is A. Output of the second flip-flop is B. Input to the first flip-flop is the OR of A and B. Input to the second flip-flop is the OR of A complement and B. The state table can be written as follows. You have A and B at time t. You have the inputs TA, TB, and the state A and B at time t plus 1. TA and TB depend on the values of A and B. TA is A or B. TB is A complement or B. Initially, AB is in state 00. and TA is 0, TB is 1. After the first clock pulse, sorry, I'm trying to find the proper way to write the states. Alright. I was going to write it in a different way, but we'll follow what we have been doing till now. So the current state is 0, 0, which means that the current input is 0, 1. If the current input is 0, the state will remain the same. So TA is 0, so A of t plus 1 is simply A of t, so it will stay 0. If the input is 1, the state will toggle because this is a T flip flop. So since TB of t is 1, B of t will go to 1. So B of t plus 1 is 1. If the current state is 0, 1, T of A is 1, T of B is 1. So both A and B will toggle, so I will get 1, 0 at the output. The current state is 1, 0. T of A is 1, T of B is 0. So only A will toggle, it will go to 0, B will remain the same. The current state is 1, 1. Then both of them are 1, 1. Both of them will toggle and go to state 0, 0. That is the state table. The state diagram would be as follows. Four states 0, 0, 0, 1, 1, 0, 1, 1. 1, 0 and 1, 1 will both go to 0, 0. 0, 1 will go to state 1, 0. 0, 0 will go to state 0, 1. That is the state diagram of this circuit. We'll go to problem 5.9. So for the JK flip flop, the output at time t plus 1 q of t plus 1 is equal to j into q of t complement plus k complement into q of t. Now here instead of q for the first flip flop we have a, and for the second flip flop the output is labeled b. So a of t plus 1 is, and instead of j and k we'll have ja and ka. So ja a complement plus ka complement into a. Substituting for ja we have x a complement plus b complement a. Of course we could derive the equation for the next state. If jk is 0, qt plus 1 will be just q of t. If j and k are 0 1, you will get a 0. If they are 1 0, you'll get a 1. If they are 1 1, you'll get the complement. This 1 can be written as q of t plus q complement t, and you can group the q of t's together. You will get q of t k bar plus j q bar of t. So that's where you get this from. J is x, k is b, and q is a here. So j x a bar plus, or x a prime plus b prime a. Similarly, b of t plus 1 is jb b prime plus kb prime b. jb is x, xb prime plus kb is a prime, so a prime whole prime is a, ab. Now we have to write the state diagram from this. Again, there are four possible states. Zero, 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 1, 1, 0, and 1, 1. Suppose you are in state 0, 0, so A is 0, B is 0. If A is 0, A of t plus 1 will be, if A is 0, B is 0, A of t plus 1 will be x into, let's write that down instead of just thinking it out. It's easier to write it down and then we can write the state diagram. can be in state 0 0, and you can give, there's only one input, so there's just x. The input can be 0 or 1, can be in state 1, and the input can be 0 or 1, can be in state 1 0, input can be 0 or 1, it can be in state 1 1, and the input can be 0 or 1. And it's in state 0 0, a of t plus 1 is x, so it will follow x. When ab is 0 1, a of t plus 1 is again x, it will follow. So when a is 0, x a prime plus b prime a will become x. When a is 1, x a prime plus b prime a will become b prime. So when a is 1, you will get b prime. Similarly for b of t plus 1, when b is 0, b of t plus 1 is equal to x. So when b is 0, b of t plus 1 is x. When b is 1, b of t plus 1 is equal to a. So it will be 0 0 here and 1 1 here. So from state 0 0, you either go to 0 0 or go to 1 1. You stay in state 0 0 if the input is 0, you go to state 1 1 if the input is 1. From state 0 1, you go to 0 0 or 1 0. You go to 0 0 or 1 0, depending on whether your input is 0 or 1. From 1 0, you stay in 1 0 or go to 1 1. Stay in 1 0, go to 1 1 if input is 1. From 1 1, you go to 0 1 regardless of the input. Then it is 0 or 1, you go to 0 1. So that is the state diagram for this particular circuit. We'll go to problem 5.10. So here it is similar to the previous question, except that there are two inputs x and y. Let me draw this differently. J is bx plus b prime y prime. K is B prime xy prime, JB is A prime x, and KB is A plus x prime xy prime. That is the logic diagram for the given circuit. Of course, we cannot forget the output Z, which is equal to x prime y prime plus B x prime y prime, which is A plus B into x prime y prime. You can take the x prime y prime common and write it as A plus B into x prime y prime. So that is the logic diagram of the given circuit. Next, we'll draw the state table. You have the present state, inputs xy, the next state, output z. Present state can be 0 0, 0 1, 1 0, or 1 1. And the inputs can also be 0 0, 0 1, 1 0, or 1 1. Now we just have to find the inputs to the flip flop based on the inputs and the present state. That will tell us what the next state must be. So when the present state is 0 0, J is y bar, K is xy bar, JB is x, KB is xy bar. If xy is 0 0, then J is JKR 1 0, JB KBAR 0 0. So 1 0 and 0 0. 1 0 will make AT plus 1 1. 0 0 will keep B of t plus 1 equal to B of t. So I'll get the state 1 0, and the output will be, everything is 0, so it will be 0. A, B, X, Y are 0, so Z will be 0. Similarly, you can do for all the states. You can do this, find JK and JBKB for all the state and input combinations, and also find the output, and you will get 1 0 0 0 1 1 0 1 0 1 0 1 1 0 1 1 1 0 1 0 0 0 1 0 1 0 1 0 1 0 1 0. Corresponding outputs will be 0 for the first 4 states, a 1 and 0 for the next 3 states, a 1 here and a 1 here, and 0 for the rest of the states. And from that you can write the state diagram. Zero 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 1 1 0 1 1. Okay, they are not asked us to write the state diagram. There are just too many transitions, so I won't write it. They have not asked it anyway. Part C, you have to derive the state equations for A and B. So this is the equation for A of t plus 1 and B of t plus 1. Depending on AB and XY. Can simplify this by taking this quad, this quad, one more quad, another quad. That would mean that you don't need the pink quad because all those ones are already covered. And finally, you can go group the remaining ones in a pair, and this will give you a of t plus 1 is the blue quad is ax bar, the orange quad is ay, the cream colored quad is bx, and the pair is a bar b bar y bar. Similarly, we'll get b of t plus 1 is equal to a bar b bar x plus a bar b bar into x prime x bar plus y. We'll go to problem 5.11. They are referring to figure 5.16. Let me draw the state diagram for you. And the state diagram that they are referring to is the following. Four states 0, 0, 0, 1, 1, 0, and 1, 1. From 0, 0 you go to 0, 1 if the input is 1, and 0, 0 you stay in 0, 0 if the input is 0. From 0, 1 you go to 0, 0 if the input is 0. You go to 1, 1 if the input is 1. From 1, 0 you stay in 1, 0 if the input is 1. You go to 0, 0 if the input is 0. From 1, 1 you go to 0, 0 if the input is 0. You go to 1, 0 if the input is 1. That is the state diagram that they are talking about. So initially you started out at you started out at 0, 0. Input was 0. So you went to the state, you stayed in the state 0, 0 and the output was 0. Next the input was 1. So you went to the state 0, 1 and the output was 0. Next 0. So you went back to the state 0, 0 with output 1. Next 1. So you went back to state 0, 1 with output 0. A 1 again. So you went to 1, 1 with output 0. I'll continue here. Now you have a 0. So you go back to state 0, 0 with output 1. Then there are 3 ones. So you go to 0, 1 with output 0. You go to 1, 1 with output 0. You go to 1, 0 with output 0. And then a 0 again. So you go back to the state 0, 0 with an output 1. Here you can see that the output is 1 only if you are going back to state 0 from other states. Next you have 4 ones from 0, 0 to 0, 1, 0, 1 to 1, 1, 1, 1 to 1, 0, 1 0, you'll stay in 1 0, and then you have a 0 finally, so you'll go back to state 0 0. So the output sequence is 0 0 1 0 0 1 0 0 0 1 0 0 0 1. That is all for part A. Next part you have to find equivalent states. So we compare 0 0 with the other states. Of course, it is not equivalent to 1 1 or 0 1, because in 1 1 and 0 1 there is no input that will cause it to stay in the same state. But in 0 0, if you give a 0, it will stay in the same state. Next, you compare it with state 1 0, but you see that if you give a 0, 1 0 transitions to a different state. So if you give a 1 0 0 will go to 0 1, but 1 0 will not go to 0 1. So 0 0 is not equivalent to any of the other states. Next, you check Next we check for 1 0 and 0 1 and 1 1. Let's see for 0 1. 0 and 1 0 are not equivalent, because if they were equivalent and you gave a 1, 1 0 would actually stay in the same state, but 0 1 does not stay in the same state, it goes to 1 1. Let's see for 1 1. 1 1 and 0 1 are the same. 1 1 and 0 1 are not equivalent, because if you give a 1, then state 0 1 will go to state 1 1. That means it will stay in the same state if they were equivalent, but 1 1 goes to 1 0, so they are not equivalent. Then we can check 1 1 and 1 0. If you check 1 1 and 1 0, if you give a 1, 1 1 goes to 1 0, so and 1 0 stays the same. So if they are equivalent, giving a 1 will give the same output and the same state. Giving a 0 will go to 0 0 with the same output. So 1 0 and 1 1 are equivalent states. Sorry, give me a minute. Uh, I have to check whether I'll check. I have to check something. I'll check and come back. Okay. I am back. So when we are looking at equivalent states, two states are considered equivalent if they move to the same or equivalent state for every input combination and also generate the same output. So here, if we consider 1 0 and 1 1 as equivalent states, then when you give input 0, they both move to the same state 0 0 and generate the same output 1. When you give a 1, they both go to equivalent states, because we are saying 1 0 and 1 1 are equivalent. 1 0 stays at 1 0, 1 1 also goes to 1 0. So both of them go to 1 0 and generate the same output 0. So 1 0 and 1 1 are both equivalent states. For the same inputs, they go to the same output and they generate the same output and they go to the same state. So 1 0 and 1 1 are equivalent. The way we can do this in a more systematic manner is you write the present state and you write the next state and the next state you will write it both for input input 0 and input 1, and you write the present output for input 0 and input 1. So there are four states: 0 0 0 1 1 0 1 1. From 0 0, if the input is 0, stay in 0. If it is 1, you go to stay in 0 0 or go to 1 0. For 0 1, you go to 0 0 or 1 1. For 1 0, stay in 1 0 or go to 0 0. For 1 1, you go to 0 0 or 1 1. And the inputs, it's 1. For 0 0, if the input is 1, the output is 0. Similarly, for 0 1, the output is 1. If you give a input 0, it is 0 otherwise. For 1 0, output is 1. If you give input 0, it is 0 otherwise. Sorry, when you're in state 0 0, whether you give input 0 or input 1, the output will still be 0. And for the remaining states, the input is 0, output is 1, input is 1, output is 0. So now we compare the output and the next state, and you can see that these two have the same next state and output, so they are equivalent states. One zero and 1 1 are equivalent. Now what you do, you replace 1 0 and 1 1 everywhere with simply one of them. I will keep 1 0. 0 0 goes to 0 0 or 1 0 with output 0 and 0. 0 1 goes to 0 0 or 1 1, but 1 1 is equivalent to 1 0, so it goes to 1 0 with output 1 and 0. 1 0 goes to 0 0, right, or 1 0 with output 1 0. So now that's one row elimination. We say that 1 0 and 1 1 are equivalent. Now you can check again. You see that the next state and outputs are the same. In these two cases, that is 0 1 and 1 0, both of them go to 0 0 with output 1 when you give input 0. 0 1 and 1 0 go to the same equivalent state. It is 1 1. 0 1 goes to 1 1. 1 0 stays in 1 0, but they are both equivalent states. So 0 1 and 1 0 go to the same equivalent state when the input is 1. So Again, these two 0 1 and 1 0 are also equivalent. Now we can say that 0 1 1 0 and 1 1 are equivalent, and obviously they will be different from 0 0 because the output will be different. Output is 1 0 for all the other states, it's 0 0 for state 0, so they're not equivalent. So you can reduce this to 0 0 and equivalent state 0 1 1 0 1 1. If you give a 0, it will stay in the same state. If you give a 1, it will go to this equivalent state. If you give a 0 from this equivalent state, it will go to 0 0 with output 1. If you give a 1, it will stay in the same state with output 0. So that is the simplified equivalent equivalent state diagram. Part C, you have to derive this using D flip flop. So there are two states, there are four states. So you need two flip flops, DAA, DBB. For this, we write the previous state and the next state, and the outputs are, we have a combinational circuit to produce outputs that are connected to the inputs of the D flip flop. So from 0 0, if you give a 0, it should go to 0 0. From 0 0, if you give a 1, it should go to 0 1 1 0 or 1 1. Let's come back to that later. 0 1, when you give 0, you have to go to 0 0. 1 0, when you give 0, it has to go to 0 0. 1 1, when you give 0, it has to go to 0 0. Now all other transitions should go to some equivalent state. And I will take that equivalent state to be 0 1. So regardless of what the previous state and inputs are, I'll keep the output A to 0. A3 plus 1 should always go to 0, so dA should always be 0. And dB just follows x. So I can give x to dB. And this will give me the required circuit. So what will happen here? Suppose you start out at state 0 0. That is a okay. You start at state 0 0. If you give input x is equal to 0, then dB is 0, so dA dB will be 0 0. So after a clock pulse, AB will be 0 0. So if input is 0, you are staying in state 0 0. But if input x is equal to 1, then dB is equal to 1. So after the clock pulse, B will be equal to 1. So it will change to the state 0 1. And if it is in state 0 1 initially, and if you give x is equal to 0, then dB is 0. So after the clock pulse, it will go to 0 0. So giving a 0 makes 0 1 to state 0 0. If you give a 1, then dB is 1. So after the clock pulse, B is equal to 1. So it will stay in state 0 1. So there are only two states here, 0 0 or 0 1. And the output is 1 only if you are transitioning from the state 0 1 to 0 0. Actually, there are only two different states for AB, since all other states are equivalent to 0 1. There's a state 0 0 and there's state 0 1. And depending on the input, 0 0 will go to 0 0 or 0 1, 0 1 will go to 0 0 or 0 1. So that's the truth table. All other conditions are invalid. Now the output is just 1 if there is a transition from 0 1 to 0 0. That is if x is 0 and AB is 0 1. In all other cases, output Z is 0. So Z is simply A bar B X bar. Right, that's it for problem 5.11. That's the end of today's session. I'll continue with the problems in chapter 5 in the next session.